What is the practical need addressed by continual learning in machine learning models?
The practical need addressed by continual learning in machine learning models is the ability to update the model with new knowledge without forgetting the knowledge obtained in the past. Continual learning tackles the problem of efficiently learning from new data while retaining previously acquired knowledge. It allows machine learning models to adapt to a sequence of datasets over time, avoiding the inefficiency of training from scratch each time new data is introduced. This is crucial for real-world applications where models need to continuously learn and improve without losing the information learned from previous experiences.
How does prompt tuning differ from traditional memory-based methods in continual learning?
Prompt tuning differs from traditional memory-based methods in continual learning by not requiring the storage of past data. Traditional memory-based methods, such as replay-based methods, store previously seen data and replay it during training on new data. In contrast, prompt tuning does not store past data, but instead prepends trainable soft tokens to the input embedding space. These soft tokens are initialized randomly and are used to guide the model's learning process without the need to store actual data. This approach reduces the computational cost compared to memory-based methods that require storing and accessing large amounts of past data. Additionally, prompt tuning focuses on updating the model with new knowledge efficiently without forgetting past knowledge, while memory-based methods may struggle with catastrophic forgetting when dealing with a large amount of data over time.
What are the specific benefits of using LoRA in continual learning compared to prompt tuning?
The specific benefits of using LoRA in continual learning compared to prompt tuning are evident in the experimental results presented in the paper. The main advantage of LoRA over prompt tuning is its higher performance, as shown in the experiments where LoRA-based variants outperformed prompt tuning variants across all benchmarks. For example, in the L2X family, L2L improved over L2P by an average of about 58%, with a significant increase in performance on domain net. Similarly, in the SX family, S-LoRA was better than S-prompts by about 60% on average, with a notable improvement on Core 50. Additionally, LoRA is almost as parameter efficient as prompt tuning, but significantly more performant, making it a more effective choice for continual learning tasks. The results indicate that LoRA can achieve higher performance without sacrificing efficiency, making it a superior option for continual learning compared to prompt tuning.
How are the S-prompts and learning to prompt L2P algorithms different from each other in terms of prompt allocation and utilization?
S-prompts and learning to prompt L2P algorithms differ in terms of prompt allocation and utilization. S-prompts allocates a new set of prompts for each input dataset, where a new trainable prompt and output head are assigned and trained on the new dataset while keeping the base model frozen. This results in independent parameter-efficient expert models for each dataset. In contrast, L2P allocates a fixed-size pool of prompts that is shared across all datasets. Prompts in L2P are selected based on the input through a retrieval step, where each prompt is associated with a key vector in the base model's embedding space. The prompts with the highest similarity scores are concatenated and prepended to the input. Additionally, L2P uses a single shared classifier head during training, jointly optimizing the prompt tokens, key vectors, and classifier parameters. On the other hand, S-prompts assigns a new output head for each dataset, leading to multiple independent expert models.
What datasets were used to evaluate the performance of S-LoRA and L2L in the experiments?
The datasets used to evaluate the performance of S-LoRA and L2L in the experiments were Core 50 and DomainNet for domain incremental experiments, and Split CIFAR 100 and Split Tiny ImageNet for class incremental experiments. Core 50 is a benchmark for continual object recognition with 50 classes from 11 datasets, while DomainNet is a benchmark for image classification with 6 datasets. Split CIFAR 100 and Split Tiny ImageNet refer to splitting CIFAR 100 and TinyImageNet into 10 non-overlapping subsets. These datasets were chosen to assess the effectiveness of LoRA and L2L in both domain incremental and class incremental learning scenarios, showcasing their performance in different continual learning settings.
What are the shared optimization hyperparameters between SPrompts and LoRA in the study?
The shared optimization hyperparameters between SPrompts and LoRA in the study include the optimization hyperparameters from the SX family. Specifically for SPrompts and LoRA, the optimization hyperparameters used are from the SX family. This means that the hyperparameters for both SPrompts and LoRA are the same as those used in the SX family. Additionally, the hyperparameters for SPrompts and LoRA include the number of clusters set to 56 in the domain incremental settings and twice the number of new classes for the class incremental settings. Furthermore, for LoRA, a LoRA rank of 57 is used as a shared optimization hyperparameter with SPrompts. Therefore, the shared optimization hyperparameters between SPrompts and LoRA in the study are those from the SX family, including the number of clusters, the number of new classes, and the LoRA rank.